clearly, right? Okay, thank you so much. I want to welcome you to another theory of statistics class. Of course, it's getting complicated, and I will advise you come to class from time to time. You ask questions. I want to believe if you attend my class, you pay attention and you ask questions, you're actually going to be fine. I started posting my recordings on my YouTube channel. So make sure because I have a lot of videos on my YouTube channel, make sure it is the one that I post at 5101/4/2025. Does that make sense? Okay, today we're going to be focusing on probability model. I prepared this material for Monday, but I decided that I was not going to rush you. Okay, so we want to focus on probability model. Today, there's going to be a lot of derivations, algebraic derivations. We're going to go more mathematical, and that's why I needed to pay attention. Uh, the last announcement I'm going to make before I get started, of course, my office hour for the first office hour for the semester will start tomorrow. I put that on the announcement section. My office hour is always Tuesdays and Thursdays. I put the time on the, but the first in the semester will start tomorrow. You don't need to be physically present in my office hour. You can join through the Zoom. The link is actually shared on Canvas. I want to welcome you to a probability model. Of course, in the outline, I'm going to discuss the concept of probability spaces, probability measures, probability models in general, and with some exercises. Those of you at that corner, can you see this very well? Okay, because I also want to write on the board. Okay, I want to use a combination of the two. So in case that is not visible, please let me know. Now, I want us to get started. Let me tell you this. What we're starting today, is going to be complicated, and it will require some theories, mathematical theories. But when you pay attention, like I said, you're going to be fine. But let me tell you, there's always going to be a kind of, story around this concept. If you pay more attention to the stories, you're actually going to get the information. So please pay attention. They are connected. I'm actually going to start from experiments. In a stochastic world, we perform experiments. Experiment does not necessarily mean you are in your physics lab. Does not necessarily mean you are in biological lab. Life itself is an experiment. Whatever we do that leads to an outcome is an experiment. Does that make sense? Okay, but let me tell you this. I'm actually going to know there's a variation in this word because when I perform experiments repeatedly under similar condition, I get different results. I'm going to say that again. When experiment is performed repeatedly under similar condition, I get the same result. I get different results. Okay? Now, that kind of experiment is what we call random experiments. Okay? A random experiment is an experiment that is performed repeatedly under similar conditions. You perform experiment repeatedly under similar conditions, but you are generating different outcomes. That's what we call random experiment. That is typical to you are in a company where they use the same machine, but what the machine produced today is different from what the machine produced yesterday, despite the fact that you are using the same machine. That's a random experiment. Does that make sense? Now, in a random experiment, okay, we're able to know that, the state of nature is multi-state. We have a multi-state of nature. Okay, we have a multi-state of nature. In a multi-state of nature, it means different things will happen, even when you perform the experiment repeatedly. Different outcomes will happen. And that is telling you we live in a multi-state environment. But when you talk, there's another environment that we call single state. In a single state environment, okay, the same thing will happen in different days. We call that a single state. Then in that environment is deterministic. This environment is deterministic. Deterministic. There is nothing to worry about in this environment. Imagine every day we laugh. Every day we do the same. Every day we're in a joyful mood. That environment does not exist. Okay? And that environment is a one-state environment. But we find ourselves in a multi-state environment. And how am I able to know that the environment we find ourselves in multi-state? I know through random experiments. Okay? Because I know there are possibility, there are different kind of outcomes that we are likely going to have in a random experiment. Now the question now is, if I want to secure the situation, as human being, if I really want to know, if I want to have an understanding of, how things will happen, okay, then what do I need to do? Then I need to use probability model. Probability model, okay, we normally use probability model to depict, okay, events, the occurrence of events, in a stochastic environment. So we're going to use probability model. So the probability model, okay, is a mathematical framework to represent random phenomena. Okay, now there's a particular structure used by a probability model. That structure is called probability space. Do you see the way they are connected? If you get the way they are connected, you're actually going to be fine. Okay, I just mentioned probability model. Probability model is a mathematical framework, okay, that we use to depict, random phenomena, okay? And I said, we need a structure. We need another line structure to be able to do that. And that structure is probability space, okay? That structure is actually probability space. Now, I want to focus on probability space right now. Please pay attention. When I talk about probability space consists of triplets. And what are the triplets that I'm actually talking about? I'm talking about this guy here. Please pay attention. Triplet, probability space. I have triplets. When I say triplets, we got three components. What is the first component? The first component, omega, is called sample space. Okay? The first component, omega, is called sample space. Like I said, the probability space made up of triplets. Okay? Made up of triplets. Okay, this guy is the sample space. What do we mean by sample space? Sample space means collection of possible outcomes in an experiment. Collection of possible outcome in an experiment. Then this guy is what we call set of events. Set of events. We also call it sigma algebra. We call this guy sigma algebra. It's a set of events. In a stochastic world, we normally have set of events. Okay, then this guy is probability measure. Okay, what is the function of probability measure? The probability measure, we assign probability to a set of events. If you pass an exam, the probability of you passing an exam is very high. That's why you pass an exam. Does that make sense? In whatever event that we have in a stochastic world, there's always going to be a measure that assigns probability value. And that measure is called probability measure. So the whole of this guy is what we call probability space. This is a probability space. Does that make sense? In a probability space where there is variation, you're actually going to have triplets. The first one is what we call the sample space, okay, that will talk about a possible outcome that we can have. A businessman or woman, somebody want to go into a business, already know the possible outcome. Go ahead.
So what's the difference between a probability measure and random variable?
Okay, what is the difference between probability measure and the random variable? You know, a random variable is a mapping function that assigns numerical values to elements in the sample space. The numerical values being assigned could be any number. But probability measure also assign numerical values, but it assigns numerical values in a consistent way, and that numerical values has to be non-negative and has to be between 0 and 1. I love that very question because the two assign numbers. Random variable assign numerical numbers. Probability measure also assign numerical numbers, but the numbers, the two of them assign are not the same. The probability measure assign number between 0 and 1. Why random variable assign numbers in real numbers? Does that make sense? I normally, I used to be happy when students ask me questions. Thank you for that. Okay, now, any question on this? Any question on this? Go ahead.
What does that say?
This one?
No, after before algebra.
Oh, this one? This one is sample space. So this notation is omega. Omega. The sample space means collection of possible outcome. I'm going to give you an example now. I want to go into environment. I want to go into weather prediction. Please pay attention. I perfectly understand my mathematics because I'm able to relate to real life. I'm going to give you an example now. Let's say, for instance, I'm talking about weather. I want to talk about weather tomorrow. Okay? I want to talk about weather tomorrow. This guy is going to tell us about the possibility of weather tomorrow. Oh my God. He's going to say it could be rainy, it could be sunny, it could be snowing. Does that make sense? This is possibility. This is an omega. This is sample space. That makes sense? Now, the calling F is going to talk about the calling F. What we have inside the calling F is more than this guy. Okay, how? You know, in the calling F, I may talk about what is the, maybe what is the chance that the rainfall value will be more than 10 mm something, or the temperature is going to be this or it's going to be that. There's a lot in the set of events. But in the probability measure, that is now going to be, according to the meteorological evidence, what is the chance of rain, what is going to be the chance of sunny, what is going to be the chance of that. Now, do you now see the difference between three of them? You know, when you relate, when you cite example, mathematics is easy. But when you are learning statistics or mathematics arbitrarily, it's not going to make sense. Does that make sense now? Okay, now, I want us to go into more example. We've been talking about sample space. Okay, my sample space may be different from your own sample space. Now, if I'm talking about tossing a coin, okay, depending on the numbers of time a coin is tossed, okay, we can generate a sample space. Please pay attention. Pay attention, okay? If you don't understand, you pay for the service, ask me question. Does that make sense? If you get stuck, okay, it's totally fine. If somebody gets stuck, that's okay. But when you get stuck, ask question. Okay, now, I want to spend more time because for you to understand the theory of statistics, for you to be able to use probability theory, you need to have the knowledge of sample space. Now, if I'm working with a coin, okay, if I'm working with a coin, if I flip a coin once, my sample space is going to be this guy. In my sample space, it's either I see head or tail. This is when I toss a coin, I flip a coin one time. Okay, this guy is going to represent the numbers of trials. The numbers of time the coin is flipped. But what if in a situation where I flip it 2 times? When I flip it 2 times, the sample space for that will be different from when I flip it 1 time. Now, when I flip it 2 times, okay, I can make use of a tree diagram. This is for the first time. If I want to go for the second time, it's going to be also the HT. It's going to be HT. Then my sample space for that, okay, my sample space right now for that is going to be head, tail, tail, head, and tail, tail. Therefore, when I flip a coin 2 times, this will be my sample space. When I flip a coin 1 time, this is going to be my sample space. When I flip a coin 3 times, this becomes my sample space. Any question on that? Go ahead.
So is the sample point just one of those?
Exactly. Oh, my God. Good job. The sample point is just one of those. But let me tell you this. There's a possibility it is only one of these that will happen. But we don't know the one that will happen. But we know the possibility. In a stochastic world, you need to know the possibility. But one of those possibilities will happen at the end of the day. So each of these is called sample point, as she said, is sample point. But all of them, we refer to them as possible outcomes. Does that make sense? Now, what if I'm playing with a die? I'm inside, we have in a die, we have 1 to 6. Okay, now the sample space, for that is just basically going to be this guy. Okay, if I flip, okay, if I toss a die once, the sample space is going to be 1, 2, 3, 4, 5, 6. Okay, that makes sense? Now, you understand what the sample space means now. I want to go to events. Okay, I want to go to events. Let me tell you this. Events is a combination of sample points in a sample space. An event, the cardinality of event is more than the sample space. Because my own event may be different from your own event. Okay, we have so many events. And that was why I said here, okay, I said an event is a set of outcome of an experiment. My event, when I flip a die once, my event may be even numbers. Somebody event may be number greater than 2. Another person event may be odd, event of odd numbers. Okay, there's so many. So event is actually a set of outcome in an experiment. And that is exactly what I'm trying to talk about here, set of all events. But let us go a little bit theoretical, and I need you to pay attention. We want to go a little bit theoretical. Okay, and I want you to pay attention. Now, for instance, if you take a look at what we have now, 1 second. Okay, now, if you take a look at what we have now, this guy is what we call the calling F. It's a notation for set of events. It's one of the triplets in the probability space. And this guy is called set of events. But you know what we want to do right now? We actually want to talk about the properties of, set of events. Okay? We want to talk about the properties of set of events. Okay, now, what I'm trying to say now is, let's say, for instance, take a look at this. Do you know what I'm trying to say? Set of events is bigger than the sample space. And I will demonstrate that to you. That set of events is bigger than the sample space. So that guy is trying to say, a sample space lies in the set of events. How? You're going to see now. Okay, please pay attention. But is there a way I can figure out the possibility of set of events? This is the way I can figure it out. For instance, if I toss a coin once, if I flip a coin once, the sample space is this, right? Now the question is, if I want to get the set of events, what am I going to do to figure out the set of events? Oh my God, we did that on Monday. The set of events is what we call the proper set. Now, on Monday I talked about, talking about what is the possible number of subsets that we can have. If I want to know, there's going to be 2 raised to power the cardinality of the sample space. The cardinality of the sample space here is 2. When I say cardinality of a sample space, I mean the number of elements in the sample space. Now, if the numbers of elements in the sample space equal to 2, then this is going to be 2 raised to power 2. Then it means the numbers of events, if you take a look at what I have right now, the numbers of events here, okay, when I do the cardinality of this guy, it is equal to 4. Now, if I now want to write it out, okay, what I talked about the other time, I said if I'm focusing on the possibility of the number of a subset in the set, I'm first going to have an empty. Okay, I'm going to have an empty. Take a look at this guy. I'm going to have empty. Okay, I'm going to have the sample space itself. Then I'm going to have situation where they occur singly. How many do we have now? We got 4. Okay, that 4 is what you have here. So now, I now need you to pay attention. Please pay attention. Okay, what are you seeing here? What is this guy? This guy is the omega. Okay, which means there is a sample space inside the set of events. Does that make sense? So sample space is a subset or a member. It's a subset of the omega. It's a subset of the calling F, the set of event. Okay, and that's exactly what I'm trying to say here. That before we can make this proposition, okay, I think I just verified that. Okay, so that guy lies in that. Okay, the sample space lies in the calling F, in the set of event. And let me also say this: if there's another set, S, and that very set S lies in the set of events, the complement of that particular set also lies in the set of events. Okay? If we have a set S, okay, that lies in a set of events, then its complement will also lies in the set of events. If I have so many events, okay, maybe I got events, I got X1, okay, X1 lies in calling F, okay, X2 also lies in calling F, okay, and I continue to go to maybe Xn lies in calling F, okay. So if we have different kind of events, okay, if we have different kind of event, X1 is an event, S2 is an event, up to Xn is an event that lies in calling F, each of them lies in calling F, then automatically, so this is going to imply their union, X1 union X2, union S3, union blah, 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 up to that, will also lies in the calling F. Their union will lies in calling F. If they are individually lies in calling F, if I actually want to write this one in the short form, I'm actually going to write XI, I start from 1 to N lies in the calling F. And that's exactly what I'm trying to say here. So right now, we're talking about the properties of events, the set of events, okay? Now, the next that I want to talk about, okay, the next that I actually want to talk about is probability measures. Don't forget, what have we been doing? We've been trying to have understanding of the triplet in the probability space. Probability space provide an underlying structure for probability model. And don't forget, the probability model is a mathematical framework to depict a random phenomenon in a stochastic environment. Okay, now we want to focus on probability measures now. Now, the probability measures, on the other hand, okay, is defined as this. Probability measure assign numbers, the same way random variable assign numbers. But the number that we assign, that is assigning, is restricted to the range of 0, 1. You can see? We have a P, that's a probability measure, that uses a function, okay, that map, okay, for 0 to 1. So a map, you know, it assigns figures, numerical values, or to a set of events, okay, in a consistent manner, and it has to be from 0 to 1. If it is outside 0 to 1, there's a violation. And let me now tell you this. If I'm talking about probability measures, can we have a rules? Can we have a rules that guide probability? Of course, yes. We have a rules that guide probability, okay? And that very rules, okay, is regarded as common goal of axioms. Common goal of axioms. Okay, common goal of axioms, they are the rules that guide probability. What is the first rule? The first rule is going to talk about non-negativity. Non-negativity. The values that is going to be assigned, it should be non-negative. We should not have a negative value. Okay, now what we're going to do is this. If A lies in calling F, if a set A lies in the set of events, okay, then the probability measure, we can figure out what is the probability of event A. And that probability must be strictly greater or equal to 0, okay, for every, okay, this guy means for every A, okay, for every A, okay, for every A, okay, the probability assigned to A should be non-negative. It should be greater or equal to 0. That is the number 1 in Kolmogorov of axioms. Does that make sense? Now, number 2, in the Kolmogorov of axioms, okay, number 2 in the Kolmogorov of axioms is actually what we call normalization. Okay, normalization. And that is going to say, okay, the probability associated with the sample space must be equal to 1. What is the meaning? It means at least one event will occur in the sample space. Does that make sense? And that's a sure event. We're sure. This is surely sure event. Okay, the probability associated with a sure event is 1. Does that make sense? And that's exactly what we mean. Okay, axioms number 2, like I said, this is axiom number 1. Okay, this is axiom number 2. Okay, now I want to go into axioms number 3 now. Okay, the axiom number 3, we talk about what I call additivity. Okay, additivity. Additivity. Okay, now if I have a set A1, it lies in calling F, lies in set of event A2, A3, and so on like that. All of them lies in the set of events. And if they are disjoint, you know what we call disjoint? Because somebody tell me for extra credits, when we say A1, A2 up to there are disjoint, what does that mean? They do not have intersection. Send me a message for extra credit. You're going to send me email, because at the end of the semester, I'm going to ask students how many extra credits you earn that will serve as an evidence. Does that make sense? The email is just going to be, I answer your question today. That makes sense? Send that to me. Okay, so A1, A2, and so on like that, they are disjoint, means they do not have any intersection. They don't have anything in common. Now, in that regard, what is the probability associated with the union? Okay, if I have a probability A1 union A2 union A3 blah blah blah, it continues like that, then it's going to be probability of A1 plus probability of A2 and so on like that. If I want to write it in short form, this is in short form. In short form, it's going to say the probability of the union of events A1, A2, up to A infinity is actually going to be the same as the sum of the respective probability. And this is what we call countable additivity. That's a common goal of axioms number 3. Now, what have we been doing? What we've been doing here is we're trying to review rules that guide probability measure. But you know what? I want to go into proposition now. Now that you understand this, I want to go into proposition now. And this is where your attention is seriously needed. Okay? Your attention is seriously needed. I actually want to, prove this guy. Okay? Proposition number 1. Proposition 1. The probability of A complement equal 1 minus probability of A. How do we prove this? Please pay attention. How do we prove this? I want to prove this using the Venn diagram. Okay, if I write A, okay, the whole of that is the omega, is a sample space, everything is sample space. This guy is A, and outside that is going to be A complement. But you know what? The sample space is A union A complement. The union between what is in the circle and the outside is going to be equal to the sample space. And let me tell you this. This guy and this guy and this guy are disjoint. Okay? A and A complement are disjoint. And if they are disjoint, we can actually use additivity rule. We can use additivity rule, okay? If events are disjoint, the probability of the union is going to be equal to the sum of the probability. So in this case, if I want to find the probability associated with this is going to be probability of A plus the probability of that. What am I using here? I'm actually using additivity, okay? I'm using additivity rule. I'm using additivity rule. because this and this are disjoint, the probability. So I'm actually going to say the probability of this guy. Okay, the probability of this guy is the probability of A union that. Okay, the probability of the omega will be probability of A union that. And of course, since this and that are disjoint, then I'm actually going, by Kolmogorov number 3, I can say the probability of the union will be the probability of that plus that. And I said something the other time. What is the probability of the omega of the sample space? It's going to be 1. This is going to be equal, or the probability of A plus the probability of this. Okay, now if I actually want to find any of that, so that implies the probability of that is 1 minus the probability of that. I'm done. That's how I can prove that. What have I done? That's a complementary law. Okay? The probability that a patient do not have a disease would be 1 minus the probability that the patient has the disease. That's what we call a complementary law. Okay, now I'm actually going to go to the second preposition. Now, when you take a look at the second preposition, okay, if A belongs to B, this class belongs to the University of Minnesota. This class is smaller in size compared to the University of Minnesota. Can we prove that the probability of this class is less or equal to the probability of Minnesota? That is the proposition number 2. How do I go about this? Okay, if I'm going to start, I'm going to start with the fact that A belongs to B. If A belongs to B, then you actually, you know, when you make use of Venn diagram, you're actually going to be, you're going to be fine using the Venn diagram. Okay, using the Venn diagram, if A belongs to B, if this guy is a omega, and I actually have this guy, and I have another guy, if this is A and this is B, okay, this actually implies A belongs to B. A is inside B, but 2 of them is inside the omega. So if you take a look at this guy now, A belongs to B. Okay, what is B? The entire B here is the same thing as B union A. When I look at the union between this guy and this guy, it's the same thing as B. Does that make sense? Now, if it is the same thing, okay, then the next, now I'm actually here now, right? If I'm here now, then if I consider what is common between A union B, what is common between the whole of this and everything? What is common? It's still this guy, right? And that is what I'm trying to say here. Take a look at that. The common between the sample space and A union B is still going to be B. It's still going to be A union B. And if that happens, if I now want to, oh my God, I want to split this guy now, that sample space is the same thing as this guy. Look at that. Look at what I'm introducing. The sample space is the same. Of course, you know, I mentioned here. The sample space is that, right? Then I'm bringing that guy in now. So I'm actually going to move from here. I'm moving from here to here. Now, the moment I move from there to there, I'm just going to apply a distributive law. Okay, with distributive law, I'm actually going to end up here. And when I end up here, what is A? This is A. What is A complement intersection B? Please pay attention. The A complement, okay, if the A complement intersection B, the A complement, if you take a look at this side, just that side, okay, that side does not include A. It is the A complement. So it's like that side is the B only. You know, there's a difference between B only and general B. The general B is everything. Does that make sense? So if you take a look at this guy and this guy, they are disjoint. Okay, inside the A and just this side, they are disjoint. When they are disjoint, I can apply additivity rule. Okay, so this guy, when I look at the union between that, okay, I can do this. The probability of the A union that guy is going to be probability of A plus that. Now, don't forget, probability of B equal to this. So, which means, what is going to make, this to be bigger than this is when this particular guy is not empty. If that guy is not empty, but if it is empty, the probability of B is going to be equal to probability of A. But if it is not empty, it's going to be greater, and that is how we know. Okay? Now, the next that I actually want to talk about is this. Let me tell you this. If the probability of the sample space is 1, then the probability of emptiness is 0. Go ahead.
For the previous proposition, can you explain again how the distributive law makes those two sides equal?
Oh, okay. I should explain again how distributive law works, right? Is that what you mean?
Yeah.
Okay. This is what happened. If I'm here, give me 1 second. If I'm here, by distributive law, it is the same thing as this. What has happened? Initially I have A union A complement. I have A union A complement, okay, intercept A union B. If I want to use a distributive law, okay, I'm actually, there's A here, right? There's also A here. I can just use a single A. So that is why if you take a look at this, it's like I'm bringing out the A that is common. There's A here, there's A here. Then I'm going to write the union, okay? Why am I putting the union out? Because the union is also common. It's like I'm factorizing. And what I'm going to have here now is going to be this guy and the factorized one. That makes sense? We factorize. That's where that guy works. Now, finally, I'll quickly talk about proposition 4. And I need you to pay attention. Okay? Please pay attention. In the preposition 4, I'm going to add a recording to quickly explain 3 slides because of my time. Make sure you watch the recording. Where I stop in this lecture, I will continue recording that in my office. Then I'll put that on the YouTube. But you know what I want to do now? I quickly want to go over preposition 4. I want to use 7 minutes to do that. 9:05 to 9:55. I want to prove this guy. And I need you to pay attention. Proposition 4. Probability of A union B equal probability of A plus probability of B minus probability of A intersection B. We want to prove. We want to have it proof that the probability of A union B is going to be equal to that. If you want to do the proof, use the Venn diagram. Okay, write this guy. Write this guy. This is A. This is B. Okay, this is A intersection B. But let me tell you this. Inside here is, if the entire circle is A, the entire circle is B, then inside here is A only. A, B complement, and inside here is A complement B. This A is the entire circle. This B is the entire circle. But inside here is A only, not B. There's no B here. Inside here, it is B only. There's no A. Okay? Now, if I have that, don't forget the omega is everything. So, what I'm going to do now, okay, A union B, if I actually want to get A union B, okay, the A union B is actually going to be A intersection B complement union A intersection B union A complement intersection B. Okay, that would be A union B, everything. But these guys, they are disjoint. This guy is the joint, this guy is the joint, then I can apply additivity rule. So the probability of A union B now is now going to be the probability of this plus the probability of this plus the probability of this. Here, I'm actually using additivity rule. Just because this guy, and that guy, they are disjoint. I'm actually calling this equation 1. If I call that equation 1, okay, what is this guy? Do you know that this guy, if I want to talk about this guy, is going to be A minus this guy. A is the whole of this, right? So this is going to be probability of A, okay, minus this. So this guy is the whole of this minus that. So I'm going to call this guy equation 2. Now, I also want to talk about this guy. The probability of this guy, okay, is going to be the probability of B minus this. I'm going to call that equation 3. If I'm focusing on only this guy, it's going to be the entire B minus that. What am I going to do now? Oh my God. I'm going to plug in equation 2 and 3 into equation 1. So plug in equation 2 and 3 into equation 1. Now, if I want to plug in that, I'm actually going to write the probability of A union B equal, instead of writing this guy, I'm actually going to write all this. So which is going to be probability of A minus probability of this, okay, plus this guy, okay. If I want to write this guy, I'm actually going to write this guy. So it's going to be probability of B minus that. Okay, now I want to solve this algebraically. This, cancel that. Okay, what do I have finally? I have the probability of A union B equal to this guy, okay, plus this guy, minus this guy, and that's already proved. Like I said, we are now going highly mathematical. But don't be scared. When you attend my lecture and you listen, you're actually going to get it right. This is where I'm going to stop today. Is there any question before I go? Make sure you stay safe. See you on Friday. Bye for now, everyone.